So, as usual, so let me just start by reminding you what we did last time, just a very brief recap. So, what we are looking at is just n independent Brownian motions, all starting at the origin, and for simplicity one dimension, but you can do it in any dimension. And this is space-time. We look at the trajectory. So, essentially, they evolve freely up to a random time, let's say tau 1, which is drawn from an exponential distribution with rate r. And then you simultaneously reset them all back to the origin. And this is like, in the example of the experimental setup I was talking about. So, it's like you let the particle diffuse and then you have a trap, optical trap, which you just close it essentially. You close it means that it goes into the origin. And you do it with rate r, which means that this interval is distributed as e to the power minus r tau 1. And then again, you let them evolve freely up to another random exponential time. And again, you reset. And you keep on repeating this process. And what we showed last time is just by using simple renewal theory that this object, this system, basically, in the long time limit, it approaches a stationary state. And in the stationary state, we have a point process. So this is the, you have n particles, so the positions of the n particles. And this joint distribution is exactly given by this expression here, where this tau is interpreted as the time since the last resetting, because you didn't care what happened before that. So from this time onwards, it was just a free propagation. So therefore, you just have a product of the Gaussians with the Brownian propagators. And then you have to average over all possible random values of this tau, the time since the last resetting. And that was just exponential distribution. And you integrate over from 0 to infinity. And that gives you the stationary distribution. And the stationary distribution has this so first of all, it means that the particles are correlated, and because you cannot write down this as a product, not as a product measure, which indicates that it's a correlation, they are correlated, and we actually computed the correlation function. And so in general, so this has the structure of what we call the conditionally independent and identically distributed, which means that basically whenever you can write down the joint distribution of this form, where this is a product, IID distributions conditioned on this random variable u, and this u is drawn from some PDF h of u, and then you have to integrate over u. So for a given u, they are of course independent, but when you integrate over u, it's no longer independent, and the correlation comes from this common shared variable u. So that's the sort of main point about this CIID structure. And in this example, what we saw is that the CIID structure came out quite naturally from the renewal interpretation, where this u variable is just the time since the last resetting, and therefore h of u is just exponential r e to the power minus ru, and we have this propagator of Brownian. So of course you can do it for any arbitrary, it doesn't have to be Brownian, it can be any dynamics. For example, it can be Levy flights, or it can be whatever you want. All that will change is just a free propagator, okay? But as long as this is a Poissonian distributed trip intervals, so this will be always r e to the power minus r tau. Okay, so here one thing I want to emphasize, that I did not put in by hand the fact that this tau has an exponential, that this tau, the relevant variable, the u variable, it came out automatically. I didn't put in by hand, basically. Okay, it came out of the renewal structure. Okay. Now, in many models, what happens is that you have a stationary distribution. By the way, this is also a non-equilibrium stationary state, because as we argued, that the dynamics violates statal balance. Now, in many problems, and we'll see an example immediately after that, which is sort of more closer to the experimental situation, that eventually you have a, this kind of CIID structure, but it's not always, manifest, it's not always obvious what is the sort of latent random variable u. And so for that you need to do some calculation to figure out what is the latent variable u. And it's not always guaranteed that this joint distribution will have this CIID structure. The advantage of the CIID structure, as I said, that you can calculate any observable. So for instance, order statistics, the average density of states, or the gap statistics, or the distribution of the the full counting statistics, etc. Because all you have to do is to calculate them by fixing u and then just average over u. So it's actually very simple in principle, and already that gives rise to a lot of nice results, quite rich behavior for all these physical observables, even in this very simple model. Okay. So what I want to do today first is to work out in detail another example which is more sort of experimentally relevant, and where you will see that the structure of this CIID structure is not evident, not manifest, but it will come out in the end. Okay. So and then the challenge is to actually sort of unveil this hidden structure of this stationary distribution. Okay, so the example that I want to discuss today is sort of similar but slightly more complicated. So you have n independent Brownian particles as before, but in a switching harmonic trap. And this is exactly the system that Sergio Siliberto does his experiments, and I'll show you the experimental results later. Okay. So what do I mean by that? What's the model? So the model is the following. So you have a line, you have these particles here, and you have a potential which is harmonic again, but this harmonic potential, so Vx, okay, so but its stiffness can take two values, two possible values. So this is V1x, which is mu1 x square by 2, and this is V2x, which is mu2 x square by 2, and I'm going to assume without any loss of generality that mu1 is bigger than or equal to mu2. Okay. So basically, so here in this example, remember that we had just two extreme cases in some sense. We had a free diffusion, which means that this mu2 was 0, and then we are just closing the trap completely so that it's completely reset to the origin, which means mu1 goes to infinity. So mu2 goes to 0 and mu1 goes to infinity, and then it was instantaneous reset. So okay, so here I'll define first the model. So this is the limit of that. So and then what you do is that you switch the frequency, the stiffness, from one value to the other value. So it goes from mu1 to mu2 with rate r1, and its reverse is with rate r2. Okay. So then you see we recover this model in the limit when mu2 goes to 0, mu1 goes to infinity, because mu1 goes to infinity means you are resetting to a point, and also r1 goes to infinity, because once you go there, you immediately, once you reset, immediately it sort of opens the trap and let the particle flow. But this is this is the limit. In this limit, we get back the previous model of stochastic resetting. But experimentally, it's much more easier to do with general mu1, mu2, non-zero and not zero and infinity. So this is a very special limit. Of course, in this special limit, we had a very simple structure of the stationary state, and we could calculate everything explicitly. But now we want to study this model with a general mu1, mu2, and general r1, r2. So what this means is that you are looking at n. So suppose the xi t is the position of the ith particle. So then essentially what it does in this model so these eta its are just zero mean Gaussian white noises, independent. This is the Kronecker delta ij. Okay, so they are completely independent. But this mu t, it fluctuates between two values. So in other words, if I plot this mu t, it's a stochastic process by itself. So it fluctuates between two values. So let's say this is mu1 and this is mu2. So it stays in mu1 for a random time, then it switches to mu2. Stays there for a random time, then switches to mu1 again. So it's a telegraphic process. So this is a dichotomous. Dichotomous means taking two values. And these guys, odd and even intervals if you like. So this guy, for example, I mean it's distributed. So let's say this is tau 1, then probability distribution of tau 1 is just r1 e to the power minus r tau 1, and these even ones, let's call them tau 2. So then tau 2 is distributed as r2 e to the power minus r2 tau 2. And then it just alternates like that. Okay, so it's between two values, taking two values mu1 and mu2.
Question. So experimentally, it seems easier to have that oscillate with a fixed period, like just to be mu1 for time.
Right. So I mean, what I want to show you is that actually to get the stationary state, see, otherwise you'll get a time periodic state. To get a really stationary state, you have to have a stochastic interval switching, basically. Okay, so that's the model, and I want to know precisely that what is the probability distribution of xi at time t, in particular t goes to infinity. So if there is a stationary state, so what is the stationary state? So this is somewhat similar. I don't know if Julien in his first week, if he covered, sometimes people study these so-called run and tumble particle, active particles. So those run and tumble particles are slightly different. So there, for example, if you take a run and tumble particle in a harmonic potential, so there the potential is not changing, but the noise itself is a telegraphic noise. So with velocity v0, it goes in one direction, and then after an exponential time it switches, it goes to the minus. So sigma t here was a telegraphic process taking values between -1 and +1. And again, these intervals are exponentially distributed. You can make them different, like this R1, R2 here. But there, the driving process was a noise, whereas here, the noise is just a Gaussian white noise, but the mu t itself is a telegraphic process. So that's the difference. So this guy also goes to a stationary state, which is known, well known, but we want to compute this first. Okay, what is the stationary state of this problem? So this is the Okay. So how do we actually solve this? So this, okay, so this is, so I'll show you how to obtain an exact solution of this model. And this is a work that was done by PhD student Marco Biroli. Quite recent work last year. Okay, and as I said, this is a generalization of the simultaneously resetting model. So you see that immediately that when R2 goes to infinity, that means this thing just happens instantaneously to mu2 is 0. Yeah, mu2 is 0, so it goes there, and immediately it gets free, and so on. Okay. All right. So how do you actually solve this problem? So unfortunately here, unlike this problem here, I cannot use the renewal approach, because renewal, one of the things that we used is that after the immediate resetting, so you don't have to keep track of the previous position. So essentially from here, they're all coming back to the origin, and therefore this guy is just a free propagation from the origin. Okay, but here, because it's a finite time thing, interval, so during this interval it propagates, and you have to keep track of the positions of the particles at the end of each time interval. Okay, so it's a much more difficult problem in general. So to solve this problem, so first thing you have to identify how am I going to write down the sort of first what equations I have to write down. So the approach will be basically the Fokker-Planck approach. That's a standard but you realize that the state of the potential or environment, if you like, is either state 1 or state 2. So I have to somehow keep track of that process as well, in addition to the keeping track of the particle positions. So it's useful to define, and I'll use the vector notations now for all x1, x2, x3, xn. So I'll define this pair of quantities p2 of xt. So this is the probability, joint probability density that, okay, I'll be a little bit sloppy. I mean, these are random variables, but I'm just using it as a variables so that the particles are at x at time t, and the state of the potential or state of the environment is mu1, and this is exactly the same. It's just only the state is mu2. So if you first define these two objects, p1 of xt and p2 of xt, then you can actually write down quite easily a Fokker-Planck equation. And let me first write down these equations, so, and then you can explain. So obviously there will be a diffusion term, okay, and then there will be advection term because of the potential. So since this guy is in state 1, so therefore you will have this is the standard Ornstein-Uhlenbeck thing. So this is P1, sorry, this is P1. And then you have minus R1 P1 plus R2 P2, okay? Because if you are at P1, so this is the usual terms, okay, diffusion and the potential term. And then there's with rate R1 you are going away from P1, and with rate R2, if you are at P2, with rate R2 you are coming back to P1, okay? So that's the equation for P1, and similarly and you start from the initial condition. So let's say with probability half, initially with probability half, I could be either mu1 or mu2. So all the particles are at the origin, and P2 is similarly. And my net probability density P1, P of xt, if you like. So this will be the sum of the two. Okay. So to solve this coupled set of differential equations, it's actually easier, convenient to first do the Fourier transform. So you define P12 kt as okay, so I define the Fourier vector k, and so then it just becomes very simple, because this guy just becomes minus dk square. You can convince yourself that there is a minus sign here. Okay, here is a ki square. Okay, so and then this initial condition there transforms into the initial condition, that is P12 k at t equal to 0. So very good. So the next point you notice, because it's a harmonic potential, there is this rotational symmetry in the problem. Because in other words, what I mean is that if you look at this equation and if you make a transformation where this Rij is a rotation matrix, where R transpose is identity, then this equation, this term here, this term is obviously evidently it's invariant, but even this term here, you can check that this is invariant under this rotation, okay, which is you would expect because it's a harmonic potential. So therefore, so what this means is that the solution, both P1, K2, and so it simplifies enormously. So it says that this guy can only be a function, I write the same function just with the abuse of notation, can only be a function of the norm of this vector. So k here is square root of so we are still not done. So then my equations are so this k square is just a sum over ki square. I'm doing it a little bit in detail, but because it's quite interesting to see how the structure comes out, because it's not at all evident that there will be a CIID structure in the stationary state at this stage. And this is also useful for the students because sometimes many problems, in particular in active particles, this is exactly the kind of technique that you need to solve a problem. So you have a coupled differential equation like this, and so in this so one thing that you notice from here, okay, so in the stationary state, I would have this equal to 0, this equal to 0. So first thing you notice that if I put k equal to 0 here, okay, then you have this relation in the stationary state. Okay. And of course, this is because the total probability is 1. So when you integrate over all leg size, it has to be equal to 1. So this means that at k equal to 0, I know my values. Which is just a balance thing essentially. This is useful, this is sort of necessary in order to solve this differential equation. So what you have then is a pair of coupled differential equation. Okay, so let me sort of write this as an operator L1 P1 tilde, which is okay. Maybe I should not do. So if I put this equal to 0, okay. So you see I can therefore write as dk square plus r1 p1 tilde plus mu1 k del p1 tilde del k equal to r2 p2 in the stationary state. Okay. And similarly here I have dk square plus r2 So let me call this operator as L1 operating on P1 tilde and L2 operating on P2 tilde. Why am I doing this? Because I want to eliminate one of them and write a ordinary differential equation for one of these variables, right? How do I eliminate it? Simplest way to eliminate it is if you define this operator, okay, like this, and now you just operate this guy with L2. Okay, now it's a full derivative, ordinary derivative if you like. But if you operate it on L2, then you see this R2 times L2P2, but L2P2 is R1P1. So essentially you will have R1, R2, P1. Similarly, you can eliminate, by operating L1 on this, you can eliminate P1 and write in terms of P2. So then essentially what you have is a second order ODE in the K space. Okay. Now question is, can you solve this? Okay, this I will not show you, but indeed you can solve it. So there will be two linearly independent solutions, and let me write down the solution first, general solution. So the general solution is P1 tilde of K okay, so you have some constant times So a1 and b1 are two arbitrary constants, and this m function is what is called mabz, is this Kumar function. Which is usually defined like a series and u is the confluent of a hypergeometric function, which is its cousin. Okay. So you have to first decide, how do we fix these constants? So that's where this relation is important, because when, okay, I didn't define what is capital R1 and capital R2. So capital is just the renormalized rates. Okay, so that's the solution, and so now I have to decide the constants. So the point is that, so you have to look at what happens when k goes to 0. So the function m, when its argument goes to 0, it goes to 1. Okay. While this function uabz, you can check that it behaves like z to the power 1 minus b. Okay. So when z goes to 0, if b is less than 1, sorry, if b is bigger than 1, then it diverges. But you have this condition here that at k equal to 0, it has to be a constant. Okay, so this guy, if you take this, as k goes to 0, because this is bigger than 1, b, so therefore, this guy will diverge, and therefore you want, this fixes the constant b1 equal to 0. And the constant a1, you can, fix from this overall normalization constant. So a1 is fixed from normalization. Okay, so therefore the full solution is, I can get rid of this. And this a1 is just and similarly p2k will be just exchanging R1 and R2. Okay, so that's your solution. Now, do you see any, CIID structure here? You don't, at least I didn't see it. So, and to make, to understand the correlations between in the stationary state, so you need to somehow invert this Fourier transform. Now that looks terrible. How can we explicitly invert this Fourier transform? And here and that's why I'm saying that it's always, sometimes it's hidden, you don't see it immediately, but you have to look for, so there is a very nice integral representation of, let's say, some constant ck square. So if I put z equal to c minus ck square, these are gamma functions. So So this is a sort of, you can find it in the standard books. This is the integral representation of this Kumar function. Okay, but this is great because then you see that this guy, you can write it as some integral, and then you have e to the power minus c k square, and there will be another factor of minus k square will come from there. But the k square, then you can invert just by this, usual. So this is the Fourier inversion of k goes to x. Okay. So therefore, we can actually really invert this full thing and write explicit this solution. So I'll just write this solution, exact solution. So this u here is this integral representation u. Then some hu, where and this hu is up to some constant which I can write down, but it's not important. Okay, so you see again, it has exactly this CIID structure, which came out thanks to this integral representation of the M function. Otherwise, we could not have guessed. So it's hidden, okay, and with some V of u here and H of u, which is quite non-trivial, because remember this capital R1 and R2 are these rates and stiffnesses. So this function has divergence or the singularities at u goes to 0 and u goes to 1, depending on the values of R1 and R2. And okay, so this is just mathematics you calculate, but then you can ask, what is the meaning of this? What is the physical interpretation of this guy u? So the physical interpretation of this u is actually very nice. I mean, so what is the So imagine that, okay, you have these two phases, right? So you have this dichotomous process, your particles are sitting in a, you have these alternative things. So you have one potential here, then it's a little bit flatter, then again this, like this, okay? And it spends time like tau 1, tau 2, etc. So let's try to understand what is this V of u, okay? So imagine that you are only in phase 2. That means your potential is just mu2 x square over 2. Okay. So in that case, and just think of a single particle first. Okay. So in that case, the stationary state of this particle, is just an Ornstein-Uhlenbeck process. So this, it will be up to some normalization. Okay. Therefore, the variance of the particle position at these things would be in phase 2, let's call it var 2, will be just d over mu2. On the other hand, if you are in phase 1, if you are only in phase 1, then the stationary state will be again some, okay, this is n2, this is n1. So the variance in that phase would have been d over mu1. Now look at this formula here. Okay. So what it means is that this u is the fraction of time that you spend in phase 2. So u is between 0 and 1. Okay. And 1 minus u, consequently, is just the fraction of time the particle spends in 1. And so this Vu is just a linear combination of these two. So this is the net variance is as if you have to multiply this guy by u and this guy by 1 minus u. And that gives you the variance of the effective process. And then Hu, then you can say, okay, can I calculate the fraction of time a single particle, let's say, spends? You have this dichotomous process. So what is the fraction of time if I go for a very large time t and I ask how this is the occupation time problem, what fraction of time it spends on one side? And so this one actually you can generalize. For Brownian motion this is known as Arc-Sine law, but here you can actually generalize. You can calculate the distribution of u, and the distribution of u is precisely given by this formula here. Okay. So that you can calculate independently. And so what you see therefore the meaning of this random variable u in this CIID structure, okay, is not completely evident. So this is CIID, and so you have to sometimes you are lucky because you could invert the Fourier transform using this integral representation and write it explicitly in this form, but sometimes it may be hidden and you just don't know how to get it. Okay, so that's a sort of interesting open problem mathematically, that if you give me I'll come to that a little bit later. So this is a very sort of nice example that you see, and you can actually make it more rigorous. I mean, you can ask, can I also somehow generalize the renewal approach to this problem? And the answer is yes. In fact, this sort of, if you look at how the x square, the variance, for example, x square changes from one phase to another phase, you can write a recursion relation. And these recursion relations are random because the tau 1, tau 2, tau 3, etc. are random. So then what you get is some kind of Kesten recursion relation. Kesten had studied this problem that, if you take, for example, something like this, some UNs are some random variables and some, you have some Vn and there are some coefficients here, I don't know, in. So imagine that you have something like this. So then ANs are random variables and you can ask, what is the distribution of Xn or, things like that. So you can generalize this, it becomes a two variable Kesten recursion relation, and using that approach you can also solve exactly and you arrive at exactly the same result. That's an alternative way of derivation. Okay, so once we have this guy here, so once we have identified our h of u and this u variable, and so then again we can calculate any observable, for this problem exactly by following the same technique that I used before. That means you just calculate it for IID variables, treating this u as a condition, as a constant basically, and you can calculate everything as we did in the first lecture. You can calculate everything, and all you have to do is to integrate over u to get the final answer. Okay, so I'll not go through the details, but just to give you just a couple of results, and then I'll come to the experiments. Please ask me, stop me if you are, if you something is not clear. Yeah.
So I'm just trying to clarify what you mean by this hidden CIID, because I guess if you started with the original problem, if yes. you condition on the entire history of the trap, if you condition on the stochastic process mu of t, then the particles are independent, conditional on the history of the trap, yes. right? And so I guess what we've shown here is that this u is kind of like a sufficient variable to capture the I don't know. Like, is there something deeper there?
No, I mean it's not. The point is that surely, I mean, of course, if you know the whole history, but the fact that it actually doesn't only a single variable, not the whole history, basically, right? So you just need to know one single random variable, and that specifies the full joint distribution. Okay. And the stationary state. That's what we mean.
So, question.
Yeah.
So can you rephrase this problem for looking at the limit distribution at infinite time t as some kind of eigenvalue problem, like you're looking for some?
No, unfortunately, no, because that's the thing. I mean, I was saying because it's a totally non-equilibrium problem, right? So the stationary state itself, you don't know a priori. Okay. So here you see that this is what comes out of the stationary state joint distribution, and this is not factorizable, so which means that there are strong correlations between particles, and but you cannot. I mean, maybe you can. I don't know. At least for now, this one you cannot interpret it as a sort of some kind of random matrix eigenvalues. First of all, there is no repulsion term you see here. See, normally, for example, when you look at the random matrix eigenvalues, I mean, as we discussed several times in this school, that you always have a van der Monde term, right? Xi minus xj in the joint distribution, which means that the probability that two eigenvalues are very close to each other goes to 0, which means that the eigenvalues repel each other. Okay. So here, of course, there is no repulsion because you just do this and it generates some correlations. Okay. But you don't know what kind of correlations. But at least in this problem, I showed in the last class that that it's an attractive correlation because when you calculate the gap distribution between two eigenvalues, I mean two particles, actually doesn't go to 0 as the gap goes to 0. Okay. Okay. So first thing is, okay, I mean, so average density as usual. This is the basic macroscopic object density profile of the gas. So you have this bunch of cloud of gas which is fluctuating between the two potentials, and you can ask what is this cloud look like here. So again, this is the rho xn, which is 1 over n delta function of x minus xi, and averaged with respect to the stationary measure. So I mean, again, from this you see that this is immediately where Vu is explicit, Hu is explicit. Of course, unfortunately, you can't do this integral explicitly, but you can easily plot it. And so it looks like this. So again, it has an infinite support. And so it's asymptotic behaviors. So it's independent of n, of course. So when x goes to 0, it goes to some constant times quadratic. So here near the top, so here it's quadratic, and it decays for large x as it's symmetric, of course. So it has a Gaussian tail, but modulated by a power law, and the exponent of this power law, it actually varies continuously with the rates R2 and mu2. Okay. So it has a non-trivial density profile, and then you can compute correlation functions and so on. But I'll not go into the details. I'll just mention just one result, which will be useful. Maybe here I'll write down. So this is the distribution of the largest eigenvalue. Okay. So again, for GUE or GOE, etc., you have heard many times that this is the Tracy-Widom distribution. Distribution of the largest position, that means rightmost particle. You can actually compute it for any second rightmost, third rightmost, etc. order statistics. but I mean, I'll just mention this here. So I'll just mention the result. I will not, but you'll see quite interesting. So the probability. So I call this M1, which is the, the maximum from the rightmost. So probability that M1 takes a value W in the limit when n is large. So this is given by RH, some constant. So this is just a scale factor. So which means that the the rightmost part in a finite sample, in a sample of finite size n, for large n, the location of the maximum, it scales like square root of log n. Okay, and this RH is just a harmonic mean of the two rates. But the scaling function f of z is highly non-trivial. So scaling function again, okay, some overall constant which I don't write, is come ugly. Where this L1 square So what does it mean? So it means that actually the distribution of the largest eigenvalue, it actually has a finite support. Okay. So if I plot the scaling function, so it's supported from L2 to L1. It has a pretty non-trivial form, is z cube here, and here at the two sides it can, okay, so it, so it can go to, depending on this, oh sorry, I forgot factors here, yes, R2 minus R1. Yeah, so this is a nice rational function, but it's to the power R1 minus 1 and to the power R2 minus 1. So you can either have both sides divergent, or you can have both sides going to 0, or you can have one side going diverging and another side go. So all kinds of behavior depending on what your values of R1, R2 are. Okay, by tuning the R1, R2, you can generate a whole types of extreme value distributions. Okay, and one thing that I should emphasize is that this is very uncommon, because I mean normally the extreme value distribution, like for IID variables, is for example Gumbel distribution or Tracy-Widom distribution for random matrix theory. So they all have infinite support. Okay, so it's very rare to actually I didn't know any result before that. I mean, if you know somebody, I mean, you can tell me that I've never seen any result on extreme value statistics which has a finite support and with this pretty non-trivial form here. Okay, so and so you can actually compute, you can calculate the gap distribution and full counting statistics, etc. But I will not repeat. It's more or less exactly same calculation as I mentioned again and again. They do it for IID. You have to be a little bit careful in extracting the large n limits, and then you have to somehow do this integral over u, or there over u, and so it's a little bit of algebra calculation. But in the end, the results are actually very rich and quite nice. Okay, so what I'll do now, I want to now go and show you this, some results from experiments. Right. So this is exactly what I said, that you can actually compute everything explicitly, and sorry, this is a different problem. Yeah, this is the problem I discussed today, and so right. So for instance, I mean, yeah, this is the extreme value distribution, and you can do simulation, as I said, you know, you can do simulation and check with the theoretical results, and you see that you can have, you know, generate different type of shape by choosing appropriately this, by varying this R1 and R2, etc. Okay. And so now let me just show you some results from the experiments of Sergio Siliberto. So as I said, you know, Sergio, I mean, okay, you know, one of the motivations, as I said, for this problem was to actually first, because in the real experimental situation, you have the particles which are in water. So these are silica particles which are immersed in a fluid like water, and there is always a hydrodynamic interaction between these particles, which are typically long range. Okay. So so what we wanted to first, you know, we wanted to understand all these observables in that system when the trap is, you know, closing and opening with some fixed rate R, and but, you know, as a control, you know, just to compare with something, experimentalists like to compare with some results, right? So as to compare with some results, we said, okay, hydrodynamic interaction is very difficult to deal with. So we just, you know, throw away the hydrodynamic interaction and just think of these particles as independent particles on a line. And then we could solve this model exactly. And now let's go back and see and compare with the experiments to see whether the hydrodynamic interaction are really important, so you don't see this result at all. Or it could be that the hydrodynamic interaction is completely masked by this dynamically generated correlation, in which case we'll see, you know, these results in the experiments. Or it could be a mixture of the two. Okay, we don't know a priori. Okay, because as I said, you know, hydrodynamic interactions are not easy to deal with. Okay, so the experimental setup is the following. So he has actually, so because these particles are, you know, kind of independent, so actually instead of, you know, putting all the particles in the same trap, what you do is you actually, because, you know, if you do that, then the particles tend to coagulate. You know, they tend to sort of form one single big particle. So to avoid that, you know, they actually separate this, they create traps which are, you know, and each trap contains only one particle. Okay, so you can do it in a controlled way. And this is typically, the separation between the two traps is about 6 microns, and the size of the particle is about 1 micron. Okay, and so you create these laser traps, optical traps, and then you can actually modulate them simultaneously. Okay, so that's like some, you know, sort of mimicking n independent particles in the same trap, because if all the traps are synchronized way, they are just closing and opening and changing values between mu1 and mu2. So this sort of mimics the system. And so first question is that, okay, we could compute exactly the correlation function that I mentioned in my previous lecture, xi square, xj square, because again, if you calculate the normal correlation function xi, xj connected part of it is 0 by symmetry, so you have to go to the next order. And so that was the first thing to measure, and that's what he did. So this is the theoretical prediction based on this model, where the particles are independent. So this the correlation is defined exactly as before. We just normalize it with variance, basically, so that it's a dimensionless object. And with this computation, you can actually compute these quantities in terms of this, you know, renormalized rates. So this is an exact formula. Okay, and we wanted to compare this with that. So the K2 is exactly mu2, this spring constant basically of the harmonic potential. And what he does, he fixes the K1 at some value 1.4 or something, and just vary K2, okay, and for different values of R. And what you see is that this C2, this function here, you know, these are the experimental points, and these lines, dotted lines, and these lines are the theoretical result from this formula. It seems to work pretty well actually. Okay, there are some error bars and things like that, but overall it seems to work pretty well, which was very surprising because we thought that the hydrodynamic interaction will be very important and we won't see this effect at all, but it's opposite actually. You don't see any hydrodynamic effect here, at least in this scale, and you see that this dynamically generated correlation is so strong, it sort of masks all the hydrodynamic effects. Okay. So that was the first surprise, and then we said, okay, we can measure other observables also, like for example this guy. Can you measure this extreme value distribution? Okay. And here is the result again. You see the K1, which is mu1, and for different values of this, you can go up to n equal to 8 particles, 8 traps, it's 4 traps and x and y directionally independent, so you have effectively n particles. And even if with n particles, n is not very large, but when you compare, so again the experimental points are those, and the theory is there, the different colors, I mean numerical, because we can actually compute our result for any finite n, and you see that it actually works very well. Okay, so the extreme value distribution. So this was for a particular choices of our such that you have a you have a dome-like structure. Okay, so that was that. So this is the sort of ongoing work, and we are now collecting more data and things like that. But it was already quite very nice to see this these things. Okay, so let me just first tell you so far I discussed 2 models. Okay, so and of course in this model, if in this particular limit you recover the previous model results, but then we were interested in this question that what about driving in different ways? You can think of many different problems, right? I mean, so how general is this CIID structure? Okay, and so for example, I mean,
quick question.
Yeah, please.
So these were 1 micrometer particles.
Yes.
Held 6 micrometers apart. Is it really that surprising that the interactions between them were weak?
No. So he has an independent way of measuring actually the hydrodynamic interactions. Okay. And you see that actually they show up in other objects, okay, but not in this C2 function basically, okay.
I see.
So which means they are there, but they don't affect everything basically. So we don't completely understand yet that why these observables are so beautifully reproduced, even though we know that there are hydrodynamic correlations which you cannot completely neglect. Okay. Okay. So what about other models or other ways of driving this kind of system out of equilibrium? And do you see this, main object here is that the environmental is fluctuation, stochastic fluctuation of the environment, and that, creates correlations between particles. So that's the sort of main point of my talk. So we looked at 2 other models. So one is classical, the other is quantum. So let me just briefly tell you what is the classical and what's a quantum model. Where should I go? Okay. So the classical model is actually very simple. So you take again, n particles in a harmonic trap. But now you don't change the trap stiffness, so Vx remains the same. Okay, so you have n particles. But the trap center, okay, let me call it Z of t. So this Z of t is a stochastic process. Okay, so which means basically if you write down the equation of motion, and Z of t is the driven. So Z of t is a stochastic process that you can choose whatever you like. For example, I mean we looked at two problems. So if you take Z of t to be exactly the run and tumble motion, that means something like this, some other constant. for instance, or you can just take Z of t itself to be a one standard Ullmark process, or whatever you like. Okay. So, and then again, in all these cases, once I not go into the details of this, but you can find in this paper that it actually goes into a stationary state, and once again you have this CIID structure, and you have to identify what is U and what is the corresponding H of U, and it works here. Okay, and this quantum model, which is the second model here, because I mean these kind of dynamics you can think of anything basically. So this quantum model is the following. So imagine that you prepare n bosons, okay, non-interacting bosons. You prepare them in a harmonic well in the ground state. So this is initial condition of your. So you have a state of the system, and I'm saying that at time t equal to 0, you prepare this system, and this is the ground state. Of these bosons in a harmonic oscillator whose center is at A, plus A. Okay. So I prepare the system there in these things, and then I evolve, because if I evolve this object with the same Hamiltonian, the evolution is trivial, right? It's just because e to the power IHT, if H is your Hamiltonian, and if you take an eigenstate of this Hamiltonian, it just gives you e to the power IETE. So it just doesn't change anything. It's just a trivial phase factor. So it's not very interesting. So when you evolve a quantum system, you should not if your initial condition should not be an eigenstate. Okay. So what we do is we prepare this in this eigenstate at plus A, but we evolve it with a Hamiltonian where the center is shifted to minus A. Okay. So that means the Hamiltonian now is half m omega square xi plus a square. Okay, so the ground state is actually the ground state is just a product of Gaussians, because it's a ground state. So product of Gaussians, but centered at plus A, and then you evolve this with this Hamiltonian up to some random time. So unitary evolution. Okay, so that means my psi of t at time t, the state will be to the power, okay, this is minus I h plus a, sorry, h at minus a, like t, and then I have this psi of 0. So I evolve up to some random time, okay, and after the random time, I reset basically. So this is called quantum resetting. So you reset back to this same ground state psi 0, and then you repeat this process, do again and again and again, okay. And again, this drives the system into a non-equilibrium stationary state. And here stationary state, by that I mean that if you look at the density matrix of the system at long time limit, it becomes time independent. And then you can actually calculate the quantum probability density. That means you evolve the system. So after a long time, so the density matrix again, if you like, you can again write some kind of renewal equation for this. So here I'm doing just normal stochastic resetting. So this is the density matrix at the long time limit, stationary density matrix. And so with respect to this density matrix, then you can actually compute, for instance, the diagonal element of this, which means x. This is the analog of exactly p of x that we are calculating, square of that. No, this is actually fine. Yeah. So this object is exactly analog of the P stationary X, and again this has this CIID structure that I mentioned, and you can actually identify the corresponding variables A and minus A and so on and so forth. Okay, and then finally you can ask, okay, what happens if I mean, as I said, both of them have this same, of course U and HU are different in different problems, but this CIID structure is always there. Okay, and finally you can ask, okay, I mean, what happens if now the particles are interacting? Okay, so here, I mean, so far I was always considering non-interacting particles. So what happens if I have particles which are interacting and then I stochastically reset them? Okay, so one example which was mentioned this morning by Ivan, which is this Dyson-Brownian motion. So Dyson-Brownian motion, as he mentioned, just if you think, it was originally, Dyson thought about this when he was actually interested in deriving the joint distribution of eigenvalues starting from the matrix. Usually, this derivation, because you have the distribution of the entries of a matrix. So let me explain this a little bit better. Here. So okay, so you have this matrix, it can be any of the Gaussian, three Gaussian ensembles, and Xij, and you want to diagonalize it, and you get the real eigenvalues, and so the distribution of the matrix entries, if you like, is exponential minus, okay, depends on, is the trace of X dagger X. So that means each elements are independent Gaussian of this up to a symmetry. And then you want to calculate the distribution of the eigenvalues from this. Okay, so it's a little bit complicated because you see here, for example, for GOE, you will have n into n minus 1 over 2 independent elements, okay? Whereas here you have only n independent elements, so that means you have to integrate out some of the other degrees of freedom, and those are usually the eigenvector degrees of freedom. So you write, make a change of variable from the original matrix entries into eigenvector degrees of freedom and eigenvalue degrees of freedom, and then you marginalize over you integrate over the eigenvalue degrees, eigenvector degrees of freedom, and if you look at the eigenvalues distribution, the marginal distribution of eigenvalues, then up to a normalization constant is this is the famous Wigner-Dyson distribution, where this beta is 1 for GOE, 2 for GOE, and 4 for GSE. And as Sylvia mentioned, that there are other, ensembles, not Gaussian, but if you have a tri-diagonal matrix by Dimitri and Edelman, you can also generate such eigenvalue distribution with arbitrary positive beta. Okay, so Dyson's original motivation was that he wanted to, this derivation is actually, it's not, okay, once you get used to it, it's simple, but, it's not so intuitive for a physicist, okay. So he actually had a different way of doing it, and what he said, okay, so these are just independent, if you like, this is just, let's say, something like this, right? Sum over I not equal to j, and then diagonal term is slightly different. So imagine that that these guys I'm doing for GOE. Imagine that these guys, that each of the Gaussian is the stationary distribution of a Ornstein-Uhlenbeck process. Okay, so you can then think of, introduce a fictitious time t. This is not real time. So imagine that fictitious time t, and then you say that okay, each matrix elements is doing an Ornstein-Uhlenbeck process. Okay. So that each of them is doing Ornstein, so each of them at long time will tend to a Gaussian, and therefore the matrix itself will go into this measure, okay? And then at each time t, I have this Ornstein-Uhlenbeck process, so I diagonalize and I get the eigenvalues, and so these eigenvalues are now time dependent, random eigenvalues basically. So it's a process which is evolving in time. And then you can, can you write down a Langevin equation for this lambda ITs such that, Then, and from that equation, you can find out what is the stationary state of that Langevin equation, and that's how we actually derived this result for beta equal to 1, 2, and 4. Okay, so that was the Dyson's original motivation. Okay, so now if you look at what is the equation which Ivan mentioned this morning, but he didn't write it down, but this is the equation. Okay, so dxi dt, so xi is the eigenvalue basically, minus mu xi, so that's the Ornstein-Uhlenbeck part, and then there will be explicit repulsion part, which says that this d times so on, and this normalization I've chosen. Actually, you can write down this equation, and there's a white noise there, and so there's an explicit repulsion term between the ith and any pair of particles. Okay, so so if you start from any ordered position, they will not cross each other, and so this is, and then this guy in the stationary state, it will go into the precisely this distribution here. And this is actually true for arbitrary beta, even though you can relate to the random matrix things for beta equal to 1, 2, 4, but for the Gaussian ensemble. But I can think of this as a particle process basically, and in the long time limit, it will actually, you can show that it will go into this stationary state. Okay, but now suppose that I do the exactly same thing, that I take this Dyson-Brownian motion. So now they are interacting. That means they are not crossing each other, and I just reset them with rate r. Okay, and again you can compute the full stationary distribution. Okay, in the so this is the stationary distribution when there is no resetting. Okay, and now the point is that you can actually with resetting also you can actually compute the full stationary distribution. I'll not show you the calculation, but this was a recent result with Marco and Gregory, and once again, what you find is that this non-equilibrium stationary state driven by stochastic resetting, it again has a CIID structure, and we can again identify these variables and so on. Okay, so this is now time for me to finish. So let me just summarize and conclude. Okay, but I'll maybe write down here the main summary. So first thing is that there's a general picture that emerges from all these different models. Which is, I mean, in retrospect, it's kind of obvious, but it's not that obvious to start with. So basically, the main point is that I'm thinking of some particles here, okay, which may be interacting or maybe non-interacting, and they're, they have a common environment. Okay. So the particles share a common environment. And then you have this second ingredient is that there is a stochastic fluctuation. So the environment is fluctuating. And because of this environment fluctuation, that actually dynamically generates strong correlations. And so much strong and long range that it even sometimes, as we saw the example of the experiments, that it masks even the other interactions like hydrodynamic interactions and so on. Strong correlations. Even if they have no direct interaction between them. So you can think of this as like a kind of some kind of stochastic control. By controlling the environment, you can actually generate a kind of a whole bunch of stationary states, non-equilibrium stationary states, or correlations between particles the way you want. So you can engineer different types of correlations by choosing how you want to fluctuate your environment. Okay. So the main point here is this dynamically emergent correlations, strong correlations. Okay. And then the second point is that the stationary state. So in most of the problems that we studied so far, I mean all the problems actually, so the stationary state, the joint distribution, so it has this CIID structure. Okay. Sometimes it's evident, it comes naturally, like in the n particle stochastic resetting, and sometimes it's hidden, like in this problem. Okay. So the question is, how general is this? Okay. Because the advantage of this CIID structure is that all macroscopic and microscopic observables you can compute very easily. I mean relatively easily. Okay. So it's good. It's a good thing to have this CIID structure. But how do I know whether something has a CIID structure? Sometimes you are lucky, but can we, if you give me a general, joint distribution, how can I know whether it, what is the necessary and sufficient condition for it to be to have a CIID structure? In fact, this is a question for mathematicians also. There are many of you here, and there is a theorem due to the Italian mathematician called Bruno Definiti, and so he has, so he had a theorem which says that if your joint distribution is exchangeable, okay, so it's a little bit tricky. So okay, so if this is exchangeable, by exchangeable I mean that if I change change xi and xj, and then this measure remains invariant. If that is so, then there is always a latent CIID structure. Okay, but the point is that it's true only for an infinite sequence. So that's a crucial part of the theorem, and unfortunately for finite n it doesn't work most often. And I'll give you an example of that, counter example. So what's the counter example? I mean, simple, again, take GOE or GUE if you like. Okay, up to some normalization. Okay. So for example, GOE, okay? So you see that this guy, obviously, if I exchange any xi, x1 with x2, let's say, or x3 with x7, I mean, this is invariant. Okay, so this is indeed exchangeable distribution, but of course it cannot have a CIID structure. Why? Because imagine that it had a CIID structure. So immediately you see that if I put xi equal to xj, right hand side is non-zero clearly, but the left hand side is 0. Okay, so his theorem doesn't work here. Okay, So this is a, for only for infinite sequence, and this is sort of open problem is, what is the sort of, necessary and sufficient condition for a finite sequence, for finite variable joint distribution, whether it has a CID structure or not. And so it's curious that there are so many physics problems which have this CID structure. And then the third thing is, okay, let's just list a couple of open problems. In all these problems that we worked out, in most of the cases, the potential was harmonic. Which had the advantage, as I said several times, that it's rotationally invariant, right? If I put two particles, it's just x1 square plus x2 square, which is invariant under a rotation. Okay. But so question is that if the CID structure is only valid for rotationally invariant potentials, or is it, so for example, you can try this problem here. Suppose I take a potential which is mod x. Okay, some constant times mod x. And I put n particles there. And I change this guy from C1 to C2. Can you calculate the stationary state? So this is an interesting open problem to see, whether this is really important for the CID structure. Or the other problem, which is how I usually start my talk, which is this, think of the simple problem of a box. So you take n independent particles inside the box, and the box, let's say the length is L, okay? And then you change from L1 to L2, and you go from L1 to L2 with rate R1 and L2 to L1 with rate R2. Okay? So it's like, you can do this experiment quite easily. Just take a piston or something and put a gas of particles inside it, ideal gas, and you just go from piston, wait for an exponential time at this length, and then go press it, do like this. So that generates correlations between the particles. What is the stationary? It's a non-equilibrium stationary state again. So what is the stationary distribution here? This also breaks the rotational symmetry, and I don't know what the solution of this problem is. Okay. So you can think of many other such problems basically. So for me, it's really what is funny. What is sort of interesting is that somehow this CID structure, which is crucial for calculating all these physically measurable observables, and it appears in all these problems. And I would really like to know what is the sort of under what conditions do you get this structure, and how general it is. Okay. So I think with that I'll stop my talk. Thank you very much for your attention. Yeah.
Questions?
I wonder if there is any consequence of CID for observables, direct consequence. For example, in the case of statistically independent variables, of course you have something like factorization, and I know it doesn't work for CID, but is there such a thing?
Yes. So for instance, one thing that would be true is like if you calculate the average density profile, it's independent of n.
Okay. Yeah. Okay.
That's the easiest check you can do.
Okay, but I guess that's kind of loose check. So
yeah, it's a loose check. Yeah, sure. But I don't know more other things. I don't know what. Other observables you can look at. I don't know. You can look at the correlation function again, xi square, xj square. I mentioned that's also independent of n. For instance, it's just a number basically. So these are two independent immediate checks you can do, but that doesn't, of course, tell you that whether it has a CID structure. Reverse is not true. So
yeah. Thank you.
Yeah.
Can I digress and ask another concept, which is determinantal point process?
Yes.
Is it remotely related to CID or
no? No. No, determinantal point process is a very different object. I mean, as it was explained many times in these things, this is basically, I mean, this joint distribution of the GUE, for example, okay, beta equal to 2, that means when you have a square here. Okay. So you see that this joint distribution you can actually write down as a determinant of some kind of kernel, okay. So it's an n by n, these things, okay. And now you can take this joint distribution and you can say, okay, suppose I integrate out one variable, okay. So I have n minus 1 variables. Can I write down the joint distribution of n minus 1 variables, okay, marginal distribution of the n minus 1 variables? For determinantal point process, it's true that yes, that is also as a determinant. It will be n minus 1 by n minus 1 determinant. But the matrix elements, the elements of the determinant is always this same function kn xi, xj, okay. So I mean, so everything depends on this kernel, and this kernel, I mean, for GUE, for example, if you go to the edge or in the bulk, the kernel has a different shape. I mean, if you are in the bulk, there's a sine kernel that Sylvia was talking about, and if you go to the edge, it has this airy kernel. Okay, it has a different form. Okay, so but there is a kernel essentially. So this is the determinantal point process. That means no matter, so you can calculate. So average density, for example, which is you keep only one observable free x and integrate out all the other guys. Okay, so that means every time you integrate out one guy, you reduce the size of your determinant by 1 basically. Okay, so if you just want the 1 point function, so that's just kn xx, and this is exactly the average density of states. Because as I mentioned, the average density of states is exactly the 1 point marginal, right? And 1 point marginal, that means you have to integrate out n minus 1 guys, and you have this, so kn x1 x1, kn x2 x2, etc. So that's a full determinant. So every time you just integrate one variable, that means it becomes n minus 1 by n minus 1 things, and then n minus 2, n minus 2. And when you integrate out n minus 1 coordinates, you are left only with one single diagonal element, which is this knxx. Okay, so therefore, if you know this this kernel, you know all the correlation functions, all the marginal densities, and including the average density and so on. So everything, okay. So this is.
Do we have such a theorem for the determinantal point process?
No, determinantal point process. You mean what is the necessary and sufficient condition for a process to be determinantal? Well, I mean it's not. I mean, okay, I don't know if there is a necessary and sufficient condition or not, but you can see you can prove some processes which are not determinantal. Okay. So it requires some special properties. I mean, so many processes have these properties. Okay. But I mean, it's not. You cannot. I mean, I don't know if you can prove really whether what is the necessary and sufficient condition for a process to be deterministic. Yeah, I guess it's a valid question to ask. If you are given an arbitrary process, unless you calculate something and verify this, is there any way to know whether it's a determinantal point process or not? I don't know. So that's yeah. Sorry. Yeah.
We didn't go into this in detail, but I was wondering if there was anything qualitatively different in the correlations for the quantum systems.
For the quantum systems, you can calculate the correlation function, but qualitatively different, I don't know actually. No, that's a good question. Yes, that's true. Yeah. So you're asking if there is a quantum effect there, basically H-bar effect. I mean, that's a good question actually. So. Okay, I haven't checked it carefully, I mean, yet, so, yeah, thanks, yeah.
Yeah, right.
The mean field solution of the Ising model has this CIID structure.
That's true, that's true, yes.
So is there some dynamics that you can propose for changing the field, or alternatively, are there some nice correlations for the spins that now that you know about these things you can do?
No, I guess you can do, I mean, you can, because, I mean, if you take the mean field model, I mean, then, I mean, I guess you can do the mean field dynamics and that will preserve the mean field structure, this kind of structure at any time t, I suppose, right? So, then one can ask a similar question. I mean, for example, okay, so I didn't show it here, but one thing you can ask, Ising model. So, oops, sorry. Sorry about this. Let me get the right. So you see, I mean, this kind of stochastic resetting is very general, right? You can take any many-body system, okay? For example, you can take Ising spins, okay? So they have their natural dynamics, which let's say is the Glover or Kawasaki dynamics. So again, I evolve it up to a random time, and then I go back, the whole configuration goes back to the initial state, okay? And then if you keep on doing this, you can ask, okay, you have this parameter R, which now drives it to a non-equilibrium stationary state. And you can ask this question like, for example, I mean, if I take 2D in D equal to 2 Ising model, okay. I know that when R is 0, so I want to draw a phase diagram. So I know that when R is 0, when there is no resetting, so there is a critical point TC here, separating the ferromagnetic and paramagnetic phase. When you switch on this R, you go to a non-equilibrium steady state. So what is the, does the critical point stays there, or what is the picture? I mean, so these kind of questions one can ask. I guess mean field dynamics also one can ask the same question, and the mean field will be easier to address because it probably will have this CIID structure at any time t, basically. So including in the stationary state. Yeah, that's a good question actually. So this is yeah. So for the Ising model, actually. I mean, I don't know if I have the reference here. Yeah, so there was this paper with Matthew Magoni and Gregory. We looked at, we just looked at the dynamics of just a magnetization basically. So, if you take a 2D Ising model and you ask, how does the magnetization itself behave under this resetting, okay? And so what happens there is that so this is a crossover line. Okay. So here it's still ferro, and here it's still para. But there is an intermediate phase here, where you have kind of, we call it pseudo ferromagnetic phase, because in that case you don't have gap, but typical magnetization is non-zero, like in the ferro phase, but on the other hand it's gapless. Okay, so it's a kind of pseudo ferro phase basically. So this is actually completely, induced by the, but nobody has studied, as far as I know, for example, just a correlation. Yeah, that's an interesting open problem. I mean, a correlation function, for example, a long range order, what happens to it? I mean, if you do resetting, so how does the correlation function behave across this critical point? I don't know. So
I suggest we continue the discussion during lunch. Thank you very much again.